In subtopic 8.2 on thermal energy transfer, the endpoint that we're getting to is looking at how solar energy is transferred from the sun to Earth. But before we do that, we need to look at some of the basics. And so we'll start off with methods of thermal energy transfer. Now, these methods you probably have come across before, but just need to make sure that we've got those basic processes under control. There's a couple of things that might be slightly different from the way that you've heard these types of thermal energy transfer being explained. But to start off with, we just need to identify that any object with a temperature above absolute zero is going to have internal energy. And the reason why that's important is that when we're looking at internal energy, that then allows us to identify what's happening with thermal energy transfer. And so I've mentioned objects there in this statement that I'm about to write now, so looking at thermal energy being transferred. It doesn't just have to be between objects. It can be that there is thermal energy being transferred from one region of an object into another, or from one region of say a gas to another. And so we're going to refer here to regions rather than objects. Now we could have those objects, those regions being located within separate objects, or they could be within the same object. So in the end, we're looking at thermal energy always being transferred from regions with high internal energy to regions with low internal energy. So there's always going to be that flow of thermal energy from high to low thermal energy. And in order for the thermal energy to be transferred in that way, there are three principal methods that we'll have a look at. Like I say, these ones are ones that you've probably covered before, but just need to revise them really quickly. Note that these ideas are also tied into Unit 3, but like I say, ultimately we're trying to get to looking at the thermal energy transfer that's related to the energy that the Earth receives. So these three principal methods. The first is conduction. Now just be aware here, conduction could refer to both thermal or electrical, so we're specifically talking about thermal conduction here. There is a bit of a link between thermal and electrical conduction, so if you think about metals as a particular example, but we're not going to bother going into that link. The textbook does if you want to have a bit more of a look, but basically when we're looking at thermal conduction, we're looking at transfer of thermal energy through a solid or between objects, and that occurs due to the vibrations of particles. And when we say particles, a couple of things to be aware of with that word. So the particles that we could be talking about could be atoms, they could be molecules, or they could even just be electrons. So any of those types of particles that you might find in matter, and that the vibration of those particles is going to transfer kinetic energy from faster moving particles to slower moving particles. So that's the method by which conduction works. Now, I've mentioned there that it's about thermal energy transfer through solids. It does also happen through gases and liquids, but the conduction through gases and liquids is far less important than this second method, which is convection. So convection is a transfer of thermal energy through liquids and gases. Now collectively, liquids and gases are known as fluids. So we could just write through fluids here, but just as a reminder, when we're talking about fluids, we're talking about liquids and gases. And the reason why we get thermal energy transfer through these fluids, it's because there is actually movement of particles. So whereas with conduction, it's about the vibrations being transferred from one to the next, this is now about the movement of particles. And when we're talking about particles in liquids and gases, we're talking about molecules or atoms. And the reason why we get that movement of particles is due to a difference in density. And while that might not seem like it's got anything to do with internal energy or temperature, it's important to note that as temperature increases, density usually will decrease. And that basically means that anything that has higher internal energy means that it's going to have a lower density, so it will sort of rise. So hot air rises is a great example of where, as temperature increases, density decreases. This also leads to convection current. So when we talk about convection current, we're really talking about the movement of a fluid due to the different densities. So a couple of examples of convection currents. In the Earth's mantle, given that the core of the Earth is quite hot, thermal energy is transferred up through the mantle, and so we end up with hotter regions at the bottom. So those hotter regions will start to move upwards, which means that the cooler, denser regions will start to move down and fill that space in behind. And so as a result, we get these convection currents where the mantle sort of loops around in these sort of circles of hotter and colder material, creating that flow of matter. Another example would be sea breezes. So you can see in the diagram on the right here, during the day we've got the air above the Earth is going to heat up faster, and so it's going to rise. Air above the ocean is going to be a bit cool because the temperature of the ocean tends to stay a bit lower during the day, and so cool air then we get onshore breezes, and so we get a convection cycle during the day that's in that direction. If we have a look then at the night, the air over the land cools faster because the land itself is cooling quicker than the oceans, and so we get warmer air above the ocean travelling upwards, and cooler air above the land sort of then filling in, so we then get offshore breezes at night. So a couple of examples of where we see convection currents in the environment. You can also see it in sort of cooking when you're boiling water and those sorts of things. The third type of thermal energy transfer that we're going to look at is probably the most important in the context of this subtopic, being radiation. Similarly with conduction, where it can refer to thermal or electrical, radiation could be thermal radiation or it could be nuclear radiation. So we've already dealt with nuclear radiation in Unit 7. When we're talking about thermal radiation, we're talking about the transfer of energy through electromagnetic radiation. And when we're talking about electromagnetic radiation, we're really talking about so light, ultraviolet, infrared, those types of radiation. So very different to nuclear radiation, where it's about beta particles, alpha particles. And the reason we get radiation is that when charged particles accelerate, and that can be electrons or ions, so when charged particles accelerate, they emit photons. And so, like I say, that's the predominant form of energy transfer that occurs from energy from the sun arriving at Earth. So it's an important point to note that while conduction and convection require matter to travel through, radiation does not. So we can have energy being transferred from the sun, whereas for conduction and convection, they actually require matter to be present in order for the thermal energy to be transferred that way. So they're the three types of thermal energy transfer to be aware of. There are a few questions that we can have a look at, past exam questions that tie into these ideas. Note that we're only dealing with them in a very descriptive manner. We're not going to do any calculations to do with conduction or convection. Radiation we'll get to in a bit more detail, looking at black body radiation in the next video.